And here we go. I can only assume that I am now live. Oh, wait. Yeah, I want to save all these details. Pink, changes saved. Okay, back to channel content. It is saying upcoming. I don't know. I don't know what's going on now. I guess I am live. I don't know. I'm still recording anyways. Doesn't matter. Okay, so I'm gonna start chapter 5. I'll upload chapter 3 and 4 later because I did it on a different channel. But I decided, you know what, I'm just gonna stick with this channel, this channel name. So we're starting on chapter 5, and chapter 5 is all about variables and types. Excuse me. I recommend you watch this video of the presentation. Okay. Either now or after reading this chapter by Ned Blanchard. Many myths about Python variables attempts to describe the language in terms of other languages. Perhaps the most annoying to Python experts is a misleading aphorism: Python has no variables, which is really just a product of someone being overly clever about the fact that Python languages uses terms name and value instead of variable. Python developers still use the term variable on a regular basis, and it evenly appears in some documentation as is part of the understanding of the overall system. However, for the sake of clarity, I will use the official Python terms exclusively throughout the rest of the book. Python uses the term name to refer to what would be conventionally called a variable. A name refers to a value or an object in the same way your name refers to you but does not contain you. Okay, yeah, it's just an assignment. Yeah. Here's a look at what I have underneath the hood. So we can start with... yeah, I just did that. So now I'm in chapter 5. Let's go. Let's first clear, and then we're going to go code. Simple assignment dot py. That is what it's called, correct. Okay, and yeah, we're just doing answer equals 42, and then we're saying insight equals answer, and then we can just kind of say print answer. And then if we go, no, that's not the button I wanted. We go over to here, and then we just say Python simple assignment .py. It should give us a 42. No such file or directly. Oh, I'm sorry, I need to save this for the first time. So yeah, if we tell it that we want it to print insight, go back over here, hit up, no such file or directory. Did I misspell it? Python simple assignment dot py. Yeah, I would need to actually like spell assignment correctly. So yeah, that's basically what it's talking about. And if we tell it to concatenate this together, and then we just change insight to 73, we hit the save. Oh, that was concatenation. Oh well, fuck it. F string it is, motherfuckers. Save. I back over to here. Clear, because you guys can no longer see it. 7342. Okay. Okay, so we can hit select all and then transfer this all out, and now it's talking about spam. And maps is equal to spam. Eggs is equal to okay, now what is it saying? Print. Oh yeah, that's gives us a whole mess of stuff. Now we need it to print spam equals maps, and then we want it to print spam equals eggs, and we save. Come over back over here. It should print double true, correct? However, if he compares back over, I don't like it when it does that. I gotta figure out a way to turn that off. But another day. Print spam is eggs. Oh, spam is eggs, and print spam is maps. Okay, and this should all, it should go true, true, false, true. Nope, all is true. Why? Because it is, if we were to add, let's say, a 0 here, save, head back over, hit that. Now we got false, false, true, true. Yeah. Okay. Names suspended both banned the same memory, but eggs would probably be bound to a different but equivalent. That's don't share an ideally. This is. It said probably false. It came back as true for me, so yeah. This operator checks identity unless you really know what you're doing. Only use this to check if something is none. Okay. As a final built-in function ID returns an integer representative of the identity of whatever is passed to it. These integers are values that the operator compares. If you're curious about how Python handles names and values, try playing with ID. In CPython, the value returned from ID function is derived from the memory address for the value. Okay. As you have likely noticed, Python does not require you, the programmer, to declare the type of variables. Back when I first picked up Python, I joined hashtag Python on IRC and jumped right in. How do you declare a data type, I asked, and within moments I received my first true introduction to the bizarre world of programming. You are a data type. The room regulars went on to explain that Python is a dynamically typed language, meaning I don't have to tell the language what sort of information to put in a variable. Instead, Python would decide the type for me. I didn't even have to use a special variable declaration keyword and had to assign like this. Okay, so now we get onto the type function. This is just telling us what it is. Okay. So now we need to code. What is this? Types. I hate this keyboard. Types.py. That gives us a new little thingy. Bam. Saved. Now it's just going to keep going. Okay, so we're going to print type answer and we need to have answer equals 42. Okay, and then back over to here, code. Python types class. Yep, okay, perfect. Next. If type answer is print what is the question? Okay, perfect. In many cases where this sort of introspection is necessary, it may be better to use is instance instead of type, as it accounts for subclasses and inheritance. The function itself returns true or false, so I can use it as a condition in an if statement. Oh. If is instance int answer print what is the question? Oh, I need to clear because I'm too far down. Right? Yeah. Should do it twice. Yep. Okay. Perfect. Next, truth be told, there's rarely a need for either. Instead, Python developers prefer a more dynamic approach. Python uses what's known as duck typing. This isn't a technical term, but it comes from the old saying, it looks like a duck, walks like a duck, quacks like a duck, then it's probably a duck. Python doesn't care much about what the value type, but rather cares about the functionality of the value's data type. For example, an object supports all the math operators and functions. If it accepts the floats and integers as operands and binary operands, then Python considers the object to be a numeric type. In other words, Python doesn't care if it is actually a robotic duck or a moose in a duck costume. If it has the traits needed, the rest of the details are probably mute. If you're familiar with object-oriented programming, particularly how quickly inheritance can get out of hand, then this whole concept of duck typing will probably be a breath of fresh air. If your class behaves as it should, it won't matter what it inherits from. Scope and garbage collection. What is this? Scope is what defines as a variable can be accessed from. It might be available to an entire module or limited to a suite or body of a function. As I mentioned already, names have scope, whereas values do not. A name can be global, meaning it has defined itself in a module, or it can be local, meaning it only exists within a particular function comprehension. Local scope and reference counting garbage collector. Functions, including lambdas and comprehensions, define their own scope. There are only structures in a language to do so. Modules and classes do not have their own scope in the strictest sense. They have their own namespace. When a scope reaches its end, all names defined within are automatically deleted. What? Okay. For any particular value, Python keeps a reference count, which is simply a count of how many references exist for that value. Every time a value is bound to a name, a reference is created. Although there are other ways the language may create references, when there are no more references, the value is deleted. This is the reference counting garbage collector, and it efficiently handles most garbage collection scenarios. Technically, Python garbage collector behavior are on the implementation. You can see how this works in a typical function like this. Okay, so new code local scope .py. Okay, so we're gonna define spam. And we're gonna have a message is equal to spam. Word is equal to spam. For anything in the range of 100, separator is equal message plus equals separator plus word tab back message plus equals separator return message plus equals spam. And then we're just gonna return message. Create the spam function inside of which I define the name message word separator. I can access any of these names inside the function. That is their local scope. It doesn't matter. The separator is defined within a for loop. The loops don't have their own scope, so I can still access it outside loop. However, I cannot access the name outside of the function. So if we come back out to here and we just tell it to print message, and then we come over to here, we hit up, and come back over to here, and we type in Python and hit enter. It doesn't know. Message not defined. Okay, yep. That makes sense. The value of the message is deleted as the function exists. However, if we come back over here, and we know that this is no longer working, and we say output is equal to the spam with no argument, and we come down here and we say print, and then we say print output, we should get that 100 times. Okay. Clear. Okay. Book is now laying flat on at page 100. No, I spoke too soon. Start flipping over again. Interpreter shutdown. The Python interpreter is asked to shut down, such as when a Python program terminates, it enters interpreter shutdown. During this phase, interpreter goes through the process of releasing all allocated resources, calling the garbage collector multiple times, triggering destructors in objects. You can use the @exit module from the standard library to add functions to its interpreter process shutdown. This may be necessary in some highly technical projects, although in general you shouldn't need to do it. Functions added via the @exit.register will be called in a last in, first out manner. However, be aware that it becomes difficult to work with modules, including the standard library. Sorry, 1 second. What is going on? Okay, so global scope, when a name is defined within the module or outside of any function, class, or comprehension, it is considered to be in a global scope, although that's okay. Therefore, you should use global scope names sparingly for variables. This is often cleaner solutions such as class. Properly using global scope names in the context of more local scopes such as a function requires you to think ahead a little. Consider what I do if I want a function that can modify a global variable storing a high score. First, I must define the variable. Okay, so we're got another thing here, and it's going to just be called global scope.py. I'm going to save this, and then we're going to first say with the high score is equal to 10. Okay. And then we're going to define score. And we got new score. Oh, what the fuck button? Oh, it's F11. That's what's been fucking up my day. Equals 465. If new score greater than high score print new high score. High score equal to new score. Score print high score. Okay, let's see what it says here. Huh. Cannot access where it is not associated with the variable. Now in the scope, it complains that I'm using a local variable before I've assigned a value for it. Problem is I'm assigning the name high score within the scope of the function score. And that shadows or hides the global high score name behind the new local high score name. The fact that I've created a local high score name anywhere in the function makes it impossible for the function to ever see the global high score name. To make this work, I need to declare that I am going to use the global name in the local scope instead of defining the new local name. I can do this with the global keyword. Okay. All right. Well, we're gonna redo this all by just going. It's not like I don't need the practice. I'm still looking at my fucking keyboard. Global high score is equal to 10. And I gotta go. New score is equal to 465. Oh. And then if new score greater than high score, print new high score, and then high score is equal to new score, and outside we're gonna hit score and then I just want to see something first. Nope. Print high score, and then if we come back over to here, we do this. Huh. Okay. Okay, so I defined it as global high score. Score, define score, colon, global high score, correct? New score is equal to 465, yes. If new score greater than high score, colon, print new high score, correct? High score is equal to new score, score, print high score. No, this didn't. Okay, define score, yes. Tab over, correct. Global, high score, correct. New score. If new score greater than high score, let's... Oh, I still haven't, under any circumstances, said what high score is. So if I do this, is this what it's saying? Okay. Okay. All right. I see what I was doing wrong. Okay. Now we get the next one. Oh, excuse me, which is going to be called global. Global score. Scope. Gotcha. Okay. Okay, so now this should print out 0. And it does. Because it's not calling... It's not returning anything, but yeah. The code runs without raising errors, but the output is wrong. A new name current score is being created in the local scope function and is bound to the value 465. The shadows the global name where the function terminates. Both new score and the local score are deleted. In all of this, the global current score has remained untouched. It is bound to 0, and that is what printed out. Once again, to resolve this problem, I need only use the global keyword. Right. So we come back down here. Global current score. Come back up to here. 465. That is correct. Okay. Okay, so that's a global parameter or global variable. Danger, there's more than one major gotcha in account for the global scope. Modifying any variable to a global level, as in rebinding or mutating on a name outside the context of the function can lead to confusing behavior and surprising bugs, especially if you start dealing with multiple modules. It is acceptable for you to initially declare a name at the global scope, but you should do all further rebinding and mutation of that global name at the local scope level. By the way, this does not apply to classes which do not actually define their own scope. I'll return to this in a later chapter, probably chapter 7. Non-local keywords allows you to write functions within functions, and I'll defer to discussing the practicality of this until chapter 6. Here I mainly want to explore this functionality's impact on the scope and consider the following example. Okay. Code non-local.py. So we're going to have spam is equal to true. We're defining the order, which will be eggs is equal to 12. Then we're going to define cook. Non-local eggs if spam print spam if eggs minus 1 print and eggs. We'll get out, and then we'll say we'll call cook, and then we'll call order, and then we'll come over here. Let's see what happens. Something's gonna happen. Okay. Function order contains another function called cook. Each function has its own scope. Remember, as long as a function only accesses a global name like spam, you don't need to do anything special. However, try to assign to a global name will actually define a new local name that shadows the global one. Non-local starts looking for the indicated name in the nested scope. If it doesn't find it, it moves to the next enclosing scope above that. Repeats until it either finds the name or determines the scope resolution. Like, I can only assume that that's what it's supposed to say, is just spam and eggs once. Right? Non-local keyword starts looking for the indicated name. Scope resolution. Python's rule about which scope it searches for a name and in what order is called the scope resolution order. The easiest way to remember the scope resolution is the acronym LEGB, which my colleague Ryan gave me. Handily numeric Lincoln eats Grant's breakfast. Local enclosing global built-in. Enclosing functions local, that is, anything found by a non-local. Python will look in these scopes in order until it finds a match or reaches the end. Non-local and global keywords adjust the behavior of the scope resolution order. Curious case of class. Classes have their own way of dealing with scope. Technically speaking, classes don't directly factor into scope resolution order. Every name declared directly within the class is known as an attribute and is accessed through the dot operator in the class or object name. To demonstrate this, I will define a single attribute. Okay. So we got a new thing. Code class attributes .py, and we're just going to hit the save. And now we're going to start off with a class Nutramatic. Output is equal to something almost, but not quite entirely unlike T. And then we're going to define a request. Self beverage. Return self dot output. Now we're outside of the class. We're typing in machine is equal to Nutramatic. Mug is equal to machine dot request dot t print mug. And then we're going to ask it to print machine.output print Nutramatic.output. Okay, so come back over here. Type in Python. What do we get? Something not on entire, something almost, but not quite, entirely unlike T, to which I spelled entirely wrong. Okay. The name output is a class attribute belonging to the Nutramatic class. Even within that class, I would not be able to refer to it merely as output. I must access it through self.output, as self refers to the class instance function, the instant method. A request is being called on, and I can also access it via machine output or numeric output. Anywhere the object machine or class numeric is respectively in the scope, all of the names point to the exact same attribute, output. Especially in this case, there is no real difference between them. Generalizational garbage collector. Behind the scenes, Python is also a more robust generalizational garbage collector that handles all the odd situations a referencing counting garbage collector cannot, such as reference cycles when two values reference one another. All of these situations and ways they're handled by the garbage collector are by far beyond the scope of this book. Moving forward, most important takeaway to remember is that the generational garbage collector occurs some performance costs. Thus, it is sometimes worthwhile to avoid reference cycles. One way to do this is within weak ref, which creates a reference to a value without increasing that value's reference count. This feature was defined in PEP 205, and documentation exists at this one. Immutable truths. Values in Python can either be immutable, or mutable. The difference hinges on whether the values whether they can be changed are in memory. Okay. Next. Immutable types, not py. Correct? Yes. I'm going to do a quick save there. We're going to come back over here real quick. We're going to hit clear. We can close, and close. Okay. We've got eggs equal to 12. Carton is equal to eggs. Print eggs. Eggs is carton, and I'll print true. Eggs plus 1. Print eggs is carton. Print eggs. Print carton. True, false, true, 13, 12. Yep. Initially, eggs and carton are both bound to the same value, and thus they share an identity. When I modify eggs, it is rebound to the new value, and it no longer shares the identity with carton. You can see that the two names now point to different values. Mutable types, on the other hand, can be modified in place. Lists constitute one example of mutable types. Okay, we're doing another one. Mutable types, not py. We got temps. Temps is equal to 87. This is fucking hot. I will make this joke till the day I die until Americans figure it the fuck out. Now this will print to true. And now we're gonna going to temps plus equals 81. Well, it's not appending to the list, so oh, it is appending to the list. Oh, I thought that would not append to the list, but apparently it does. Prints temps is high. Highs. Print highs. Print temps. Then we come back over to here, and then we hit Python mutable types. Traceback. What did I do here? Oh, whoops. So it needed to be inside of that in order for that to work. Okay, so come back over to here. We try this again. Bam. Okay, so plus minus is going to append it to the end. And I guess if you were to do a negative minus, minus equals, it would remove it. No. Unsupported. Oh, okay, because, yeah, highs is equal to temps, but temps is not... Highs is not equal to a list. No. Okay. That does not work. Interesting. Curiouser and curiouser. Passing by assignment. Passing by assignment. Another frequency. Oh, that's much better. I probably sound a little bit better now. Okay. Another frequent question from programmers to a new language is, does Python pass a value or by reference? The answer is effectively neither. More accurately, it passes by assignment. Neither values nor names bound to them are moved. Instead, each value is bound to the parameter via assignment. Consider a simple function. Define greet person, print hello person. Yep. Name, yep, greet name. Here, there is one copy of the string value JSON in memory, and that is bound to the name, my name. When I pass my name to greet function, specifically to the person parameter, it is the same as if I said person is equal to my name. Again, assignment never makes a copy of the value. The name person is bound to the value JSON. This concept of passing assignment gets tricky when you start working with mutable values such as lists. To demonstrate the often unexpected behavior, I have written a function that finds the lowest temperature in a list, which are all in freedom units. Yay, freedom units! Okay. Oh, my goodness. So much stuff going on here. And code. Code lowest temp.py. Okay, save. Define the lowest. Temperatures. Temperatures done. Sort. Print. Temperatures. In first position. Define temps is equal to 85, 76, 79, 72, 81. Find the lowest temps. Print temps. Okay. It decided that it was 72, which, yeah, I mean, that's the way that it would work. Okay. Find the lowest temps sorted as past temperature is exactly sorted one mutable list that both temps and temperatures aliased. This is a clear case of a function having side effects where it changes to values that existed before the function call. An awe-inspiring number of bugs originated from this one type of misunderstanding. In general, functions should not have side effects, meaning that any values passed to the function as arguments should not be directly mutated. To avoid mutating the original value, I have to explicitly make a copy of it. And here's how I do that in that find lowest function. Okay, so we're gonna comment all this out again. We're gonna start doing this again. Define lowest. Define lowest temperatures. And we're gonna do sorted temps is equal to sorted temperatures. And then we're going to print sorted temps. Then we'll come back over here. And nothing fucking happened. Oh, because it's still... I guess it's still wanting this. That would be my problem. I should have just... I'm reading this thing as if that's the way that it should be. And I'm not thinking about the fact that it's not the whole thing. And I'm about to sneeze. Pardon me. And then we need to do find lowest temps, and then we go print temps. Yeah. Okay, so now it's two different lists and it's printing. Yep. Oh, whoops. Yeah, that should have been there, and then that should come up to 72. Yep, okay. Sort function has no side effects as it creates a new list using the items passed to it. If you're coming from C and C++, may be helpful to remember that potential hangups related to pass by pointer or pass by reference. Though Python's assignment is scarcely similar to the technical standpoint, the risk of side effects and unindented mutations are the same. All collections, including lists. Looks like I'm building tic-tac-toe. Okay. All collections, including lists, employ a clever little semantic detail that can become a real pain in the ass if you don't know to expect individual items or references. Just as a name is bound to a value, so are the items in collections bound to values in the same manner. This binding is also called a reference. A simple example involves trying to create a tic-tac-toe board. This first version won't work quite how you would expect. I would start the game by creating the board. Okay. Well, then let's start by creating the board. Code. Tick. Tech. Go. Python. Okay. Save. Board is equal to a double list. With a hyphen in between. And outside of this, we are going to multiply this by 3. And then we are going to multiply this by 3. I'm trying to create a two-dimensional board. You can fill a collection like a list with several items, all with the same repeating value. Use this multiplication. I've done it here and close the repeating value in brackets. Unfortunately, this won't work the way you expect. The problem begins when I attempted to find the second dimension of the array. 3 copies of blank using multiplication. You can see the problem when I try to make the first move. Okay. So we're going to go board 1, board 1 0 is equal to X, and then for row in board print F row 0, and then we're going to do row 1, and then row 2, and then I'll close that off. When I mark the board, we are seeing only change. on the board in a spot like this. Okay, so I guess this is supposed to work now. Let's see what happens. That was not the way that it was supposed to work. Do. X to 2. Okay. Okay. Yeah, that's right. Python. Tic-tac-toe.py. Oh, okay, yeah. Whoops. Somehow one change has propagated to all 3 rows. Why? Yep. Initially, I created a list where 3, since the strings are immutable and thus cannot be modified in place, this works as expected. Rebinding the first item in the list, X does not affect the other 2 items. The outer dimension of the list comprises, because I defined one list and used 3 times, now I have 3 aliases for 1 mutable value. By changing that list through 1 reference in the second I am muting. There are a few ways to fix this, but all of them work by ensuring each row reference is separated. Okay. Okay, so that doesn't work. Okay, well, unfortunately, I have to go. I'll have to pick this up another time. Yeah, I definitely have to. Alright.